So the anthropic principle basically says it's impossible for us to tell the difference with just one instance of life. So without finding life other places, uh, we can't tell the difference between if we're super rare or super common. The likelihood that we might find life somewhere else can also be expressed mathematically. So Frank Drake, in the mid 1960s, came up with an idea of how you could set up an equation that would demonstrate the potential likelihood for finding life. Now, this equation wasn't actually meant to calculate how many intelligent alien species were out there. The whole idea was just to show that even with some conservative estimates, that the likelihood was there and it was worth looking. So, what this says is if you're looking for the number of civilizations with radio communication, uh, and we use radio communication just because it's a convenient way to send information throughout our galaxy. So we kind of assumed that other intelligent aliens would also use radio communications, but that's our cutoff for what we consider an intelligent civilization. And the number you would find would have to be equal to R star, which is the average rate of star formation in our galaxy, which is a known value. We know what that is, times FP, which is the fraction of planets, of the stars that have planets. Now, we didn't find the first exoplanets or planets around other stars until the 1990s. So there was a long time between this equation and when we actually got some values for hardly any of these uh, variables. And in fact, most of the variables are still unknown. So we don't know what the numbers to plug in for are. But for the fraction of stars that have planets, that's actually pretty much all of them. Every star we've looked at, we've been able to find planets around them, and most of them have more than one planet, which is the next. The next variable would be NE, the number of planets that can potentially support life per star that has planets. So this is another one that's really hard to quantize, to get a number for, because we're just not really sure. Our cutoff for being able to support life is to have liquid water. So we've got a decent estimate for some planets, but you could have a planet that's like Venus, where it's in the correct orbit to have liquid water, but Venus has a runaway greenhouse effect, so it's far too hot to have liquid water on its surface. And we can't currently tell the difference between a Venus-like planet and an Earth-like planet for most of the planets that we find. We're working on it, we're getting better. But right now, those are still pretty big estimates. The next factor, F sub L, would be the fraction of planets that could support life that actually develop life. This one we have no idea. We don't know if everywhere where the conditions are good, life pops up, or if formation of life is really difficult and super rare. The next variable is F sub I, the fraction of planets with life where the life actually becomes intelligent life, where we get civilizations. This could be really rare. There's really only one technological civilization that developed here on Earth, us, and it took a long time for our civilization to form. And it's possible that without some highly unlikely scenarios or just some probabilistic effects, that the Earth could have gone without any intelligent civilizations if things had just gone slightly differently. And then FC is the fraction of civilizations that develop technology that we can detect. So just because a civilization becomes technological doesn't mean that we can detect it if they don't make cool enough stuff. It wasn't until the 20th century where humanity actually had technology that could transmit radio waves through our atmosphere and out into space. So before then, Earth would not have looked like a technologically advanced civilization. So, and then